Hello and welcome back to the next video in our series, SPARQL 101. My name is Thomas Cook and I'm excited to take you through this presentation on how to get up and running with RDF and SPARQL. Here's the agenda of what we'll be covering today. I want to give you a quick history lesson on what are the origins of SPARQL. We'll talk about the semantic web, linked open data, and knowledge graphs. And then we'll take a look at, what is RDF, the data model, what's a URI, and what is SPARQL. And through this, I'll be giving you examples on how to use AnzoGraph and how to use SPARQL with AnzoGraph. The origins of the semantic web started with Tim Berners-Lee in this famous Scientific American article where he describes the vision of the semantic web. The early days of the World Wide Web were based on documents, people pointing and clicking through documents, HTML, hypertext, etc. But Tim Berners-Lee envisioned a web of data, and that's how the semantic web was born. The W3C is the standards body for the World Wide Web. You can see all of the different technologies that they base various standards on. They create the different standards for HTML and XML, SOAP, OWL, and also all of the technologies behind the semantic web. On the left-hand side, you can see all of the technologies for the World Wide Web, and on the right, the technology stack of the semantic web. And here we'll be talking about SPARQL and RDF and RDFS and OWL in later videos. The semantic web created the linked open data movement, where all of these different providers online were exposing SPARQL endpoints and exposing data using linked data technologies and semantic web technologies. So if you go to this website, linkedopendatacloud.net, LOD-cloud, you will see that there are over 1,200 different data sets with 16,000 links. So a huge number of open data sets out there on the world. Each one of these dots here that are represented by the legend on the side of different geographies and government, life sciences, etc., they link to each other through this web of data. DBpedia is one of the most famous endpoints on the web. It's an open knowledge graph. It's in over 125 languages. There's 3 billion pieces of information, or what we call RDF triples, and 580 million were extracted from the English edition of Wikipedia. 2.46 billion were extracted from other languages. So there's a link there to find out more about DBpedia, but they also have an open endpoint that we'll take a look at in a moment. These are some statistics on the different items that they have in their ontology, in their schema, the different classes and resources that exist in DBpedia. So you can see there's a 1.4 million persons and 411,000 workplaces and 251,000 species, etc. And so you can go and look at the various classes at that link. They also host a SPARQL endpoint. So here you can test out your SPARQL skills on an open endpoint, and all of the linked open data clouds are open endpoints, so you can get the endpoint address and pass that in to query those. And so we'll take a quick moment here to go look at the SPARQL endpoint. So here I have the SPARQL Explorer for DBpedia. So you can pull up this link here, dbpedia.org/SPARQL, and you'll come to this. And here I've written a query where we look for Robin Williams' birthday. Now, it takes some understanding to know the ontology and how to find different resources, but this is just an example of how to get this. So you type in your SPARQL query, and then you hit go, and then here it results in the date of Robin Williams' birthday. So again, there's a ton of information out there available on the web, and it's all freely queryable through these open endpoints. And this is part of the history lesson for the Semantic Web and SPARQL endpoints. That they're in quite a lot of places out there. All right, so what is RDF? RDF stands for Resource Description Framework, and it's really the data model of the Semantic Web. And that means that all data in the Semantic Web technologies are represented in RDF. So everything is represented as a triple. It's a single fact. And a triple is in the format of a subject, predicate, and object. And that's the most atomic level of data. So as a simple example, we can have sky, color, blue. This represents the sky is blue, a simple fact. So RDF is not like the tabular model in relational databases, nor is it like a tree in the XML world. Instead, it's a labeled directed graph. So I have a simple example here. We gave this presentation at Graph Day in Austin back in January. And so we have Austin here. We have Alice drives a Tesla. Alice is a friend of Bill, and Alice is a resident of Austin. This may be a whiteboard representation of the information that you want to represent in your graph. And so that is the data model. That is what the data model looks like. We can also serialize that. That means turning it into actual data that can be communicated to a database or shared in files or that type of thing. So there's different types of RDF serializations. You have Turtle, N triples, RDFA, JSON LD, there's different ones. But here we take the model that we have represented with these circles and arrows, and we represent it with these angle brackets. So you'll notice each one of the bubbles is surrounded by angle brackets. So Alice drives a Tesla. That's this triple here. Alice drives a Tesla. Alice is a friend of Bill. Okay, that's this triple. Alice is a resident of Austin. That's this triple. And then the Tesla has the color blue. Now, one thing I'll point out here is that blue is in a rectangle while the other ones are in circles. And you'll notice that blue is surrounded by double quotes and the others are in angle brackets. The reason for that is because these are actual entities, whereas blue is a literal. And so these are how you can connect these things. We still represent the literal in the graph. We just represent it separately as a box here. So there's three different types of nodes, as I just mentioned. There's a resource node, which defines a person, place, or thing, or object, or event. And then there's literal nodes, so that can be a date, an integer, a float, all different types of. Those dates are based on XSD from XML. So if you go and take a look at the XSD data types, you can find out all the different data types that are supported through there. And then there's also something called blank nodes that we'll cover in a later video. One of the nice things about RDF is that you can create universal identifiers. So your data can be unique anywhere in the world. And the way that this is done is similar to the way that the World Wide Web uses URLs to make sure that everyone has a unique home on the web. And so you can actually put a URI, what we call a URI, a uniform resource identifier, like an HTML path, right? So here we could put http example.com/resource/person #Alice. Now, if I'm working for the company example.com, I can build this path however I want and put all the different resources underneath this path, and it should never collide with anybody else out there on the web because it's under my domain name. And so this is one of the ways that we create universal identifiers, okay? And so now you can see here drives would be something more like example.com/resource/person/drives, but now our RDF serialization just got much larger. So how do we deal with that? One of the ways that we deal with that is through what are called prefixes. And so here we can create a prefix. So we want to reduce this down. And so for those long URL paths, we can create a shortcut, a prefix. So TSLAP stands for resource person. TSLAR stands for resource. And so now I can prepend that to each one of those things and it will replace that. So now I have TSLAP Alice, TSLAP drives, TSLAC Tesla. So now I have a prefix appended to each one of my things. And you'll notice that I don't have angle brackets on here any longer. That's because the prefix automatically appends those. If you use a prefix, it basically puts your item inside of here, okay? So this is the same representation as the original data, except now it has a universal resource identifier. If you're sharing this data on the web, you don't want it to collide with anyone else. Or if you're in a large organization, you want to make sure that your IDs do not collide with anyone else. Because it would be a good time to point out that each one of these URIs has to be unique, or Alice is basically your ID. So what we've done here in this example, these examples are very simplified in the RDF world to help you understand the basic concepts. And I'll explain more about that in a moment. But here we can see some of the common prefixes that are used. Each one of these links have different vocabularies defined in them for various things. And so these are common ones that you'll see used in the RDF world. Okay, RDF, RDF schema, AL, XSD, etc. So what is SPARQL? SPARQL stands for SPARQL Protocol and RDF Query Language. It's actually a recursive acronym. You don't see those very often, but they do exist. So SPARQL Protocol, it's interesting because it's a language and it's a protocol. So it defines not only how you write the query, but also how the query is passed over the internet. So it uses HTTP, it uses REST, what are the different parameters. So the SPARQL standard defines all these things. And it's really important because this is standardized. So every SPARQL endpoint, every database vendor, all of the different tool providers in the RDF ecosystem all work off of the same standard and should interoperate successfully because it's all standards based. And so what does a SPARQL query look like? Well, SPARQL is inspired by SQL. So it looks very similar to SQL. There's select, there's a from, a where, group by, order by, etc. So if you're familiar with SQL, this will look very familiar to you. So let's first insert some data. I'm going to remove all of the prefixes to make everything much more simplified. If you're just working on a proof of concept or just doing some testing in your own local instance or something like that, you don't have to have all of the prefixes, although they are a best practice. But if you're just doing simple examples, they're not required. What I will point out is that it's important that each one of your, each subject is unique. So Alice would basically be an ID. This might not be a real world case here, but just as a simple example, you would basically have some ID here in place of this. But we're just going to do these very simple examples to get you up and running with SPARQL and RDF in a quick way. So here we have insert data into graph test one. And then I put our triples that we talked about earlier. So Alice drives a Tesla, Alice is a friend of Bill, etc. So I'm going to switch over to our Zeppelin notebooks. And in the previous video, getting up and running with AnzoGraph, I showed you how to connect Zeppelin notebooks to your AnzoGraph instance so you can type SPARQL queries directly into Zeppelin and execute those against that. So if you don't have Zeppelin up and running, I recommend you look at that previous video, getting up and running with AnzoGraph DB. And now I'll make this a little bigger so it's easier to see. So here we have our query. we use the SPARQL directive. This is not part of the SPARQL language. This is a special keyword that's used in Zeppelin to denote that it is a SPARQL cell, that it's a SPARQL paragraph here that we're executing. So this is something, because in Zeppelin you can execute different query languages in this data science notebook, and so this is not part of the SPARQL language. But here is the query that's going to be executed against our database. And to run that, you can click on this run button here, or you can click Shift Enter. So I'll click run. It says the query executed successfully. And now I'll switch back over to our slides. And now it says, let's count how many triples are in the graph. So I have select count star as count. So this was the variable name that will be returned by my count from test where SPO. So these are variables down here, and it shows that the result is 4. So this is what's called a graph pattern. SPO just says match any subject, match any predicate, match any object. These are variable names, and variable names that you can define. So I could have just as easily said ABC or XYZ or subject, predicate, object. You define these variables, but this is basically matching anything in the graph. But that is the most simple graph pattern, so it should show all of our triples. And then here it says count those. So if I go back here, you can see I have the same query written here. If I execute that, we see a count of 4. Okay, well, let's take the count out and now just view all the triples. So select, go back to my slides here. So we'll select SPO from test1 graph where SPO, this is the graph pattern, match any triple. Okay, so this will return all of the triples in our database. Okay, so here you can see, I run it, and it shows me Alice is a resident of Austin, Alice is a friend of Bill, Alice drives a Tesla, and the Tesla color is blue. Okay, now let's go back. Now, we use these graph patterns to find the data that we want. So there's different ways to do this, but what we could do is match directly on the predicate here. So the predicate is, if I want to see who drives a Tesla, there's all kinds of different analytics that you can do with SPARQL, and we're just starting with the very basics, like how do we match the data that we want to find. And so in this case, I have I want to find every subject that drives a Tesla, okay? And then the result, when I run that, is I just have Alice, because in our graph, she's the only one that has a drives link, but in a real world graph, you may have millions or thousands of links between subjects that drive a Tesla or that match your graph pattern. So this is just a simple graph pattern here based on this very simple graph. And so you'll be able to download this tutorial notebook and run it yourself. And the first cell that we did will insert the data, and then you can run these example ones. We'll have a follow-up video after this one where it gets a little bit more complex. We get into some more complex examples of how to use RDF star and some other more advanced topics. But here we're just doing the very basics. So how about who drives a blue car? So this, we look at a join operation. So I want to find every subject that drives a car, and that car has the color blue. So you'll notice this first line ends with a period. That defines a triple, okay? And I have a variable at the end of that triple called car. On the next line, I use that same variable name in the subject position that links the predicate, the object of this first triple, which is car, to the subject of this one. So I'm basically saying, find every resource that has a link of drive and anything and match anything, but they could drive anything. It doesn't have to be a Tesla. It could be anything. Before we were matching only on Teslas, but here is a drives a car and the car has a color of blue. So in our case, there's only one person that drives and there's only one color that's blue. So we should get back who we expect from this one. So we know that Alice is the result here. I'll run that. Okay, and you can see that Alice is indeed the result, but this shows the join operation of combining multiple triples in a graph pattern or multiple patterns in this where clause here. Now I want to find out who drives a car and what color is it. So here I've changed our query pattern to look for any color and also to print the color in the select statement in our list of output variables. So you'll see here the output is Alice and the color is blue. And again, we can run that and show what that looks like down here. There we see Alice and the color of blue. If I move on. So the next question I want to ask is who drives a car and what's the color and year? So I have select subject, color, and year from test one. The subject drives any car. That car has a color of any color, and that car has a year of any year. But when I run that, I don't get any results. Okay, so why is that? Well, the reason why is because the year, this graph pattern does not match in our graph. You'll see that there's no link here from any car that has the year pattern. So how do we fix that? The way that we fix that is we use the optional keyword. If the optional keyword is not there, it's going to strictly enforce that year is there, because everything in your where, it's looking for everything in your where clause to exist and be true before it will return. So if you're not sure, or if you don't care if it has a year or not for that particular predicate, for that particular value, you can use the optional keyword. In this case, we do get a return value, we do get a result set, and you'll notice that the year is blank because that was optional. So that's a really key thing that can trip up a lot of new people to RDF, is this optional keyword. So be careful with that and know that it's there, because you may not be getting back the patterns that you think exist. So that is something to be aware of. Okay. And we'll take you over to the SPARQL notebook to show you. One other example I had here is we don't have to put blue. If I want to find out who drives a blue car, I can actually filter. This is a way to put a filter in on one of the variables. So this is our query that returns anybody that has any color car. We saw that Alice has a blue car. If I want to just filter out the people that have blue cars, then I type filter where color equal blue. And when I run that, I see that Alice has the blue car. Okay. Now here's our optional example. So select our subject, our color, and our year, and from any subject that drives any car that has any color, and optionally print that year of that car. So if there are, and so when we run that, you'll notice that in this case, there is no year, but if there were other vehicles that had years, you would see their years printed here. But this is just a simple example. You can go back up to the top and add that into the test here, if you like. So we can say the Tesla has a color of blue. We can copy that line and put the year is 2020. And you can make that a string or you can make that an integer. That's up to you, but you can define that way. So I'll insert that. Well, what will happen is because these other triples already exist in our graph, only this triple will be inserted. The whole insert statement will run, but because they already exist, only this triple will be inserted. We don't insert duplicates. So now if we come back down here and run this query again, we see that the year 2020 now appears because we just added that into our graph. Okay. So like SQL, SPARQL has several solution modifiers, and a solution modifier allows you to do things like order bys, group bys, halvings, limits, offset. These are things that modify the overall solution. So if you have a set of results and you want to do an aggregate meaning a sum or an average or one of the other built-in SPARQL aggregates, you can do that. If you wanted to write your own aggregate, we give you that ability through our user-defined extensions interface, and you can write your own functions or aggregates. But there's several that are built in as part of the SPARQL 1.1 language. So pretty much anything that you can do in SQL, you can do in SPARQL because it was inspired by SQL and it has pretty much all of the same functionality as the SQL query language. So these are some of the aggregate functions that you can find: average, count, group concat, max, min, sample, and sum. And as I mentioned, it's possible to write your own aggregate functions as well using our user-defined extensions interface. So if there's something that you wanted to do that it does not do currently, it's easy to extend the database to do that. Now, these are the different types of query forms that we support. So you can run a select, which will go and query the data and return all the data that matches the graph patterns and the filters and the other things that you've set up. You can also call a construct statement, which is in the place of the select. So instead of a select, you would be executing a construct statement. It's a different type of query, and it returns basically a graph. So this would return RDF. It would return the data in RDF format, RDF triples format. So this is useful for doing ELT, so writing from one graph to another graph inside the database, or exporting the data to share it with someone else. Or there's a number of different reasons why you would want to use the construct. This can also be used to build views in our database. So if you want to build a view, you can do that on top of an existing data source, and then you would use the construct state. The ask is just returns a true or false if something exists or not. So it may be a very complex where graph pattern that you've built, but it's only going to return a true or false. So sometimes you may want to query an endpoint, or you may want to query your AnzoGraph database and just get a yes or no answer if that graph pattern is satisfied. And describe is the last form of query that you can run, which will basically print out additional information about the individual subject that you've passed to the describe. All these are documented in our online documentation, so I encourage you to go and check that out. And here's some additional functions and operators that are supported. These are part of the SPARQL 1.1 standard, so you can see different logical conditionals, math, string operations, date operations, SPARQL test, etc. So a lot of different functions are built in. We have over 200 different functions that are built into the database to do various operations on strings and various things. We've even added a huge number of ancillary functions that do additional things above and beyond what's in the SPARQL 1.1 standard. So you can go and take a look at our documentation and search for what you're looking for. If you have any questions on using the AnzoGraph free edition, I encourage you to use stackoverflow.com and post your questions there, and we monitor that closely to answer your questions. Or if you're doing an evaluation of AnzoGraph, we'd love to hear from you, get you set up with the Enterprise Edition so you can run on any size hardware, on any size cluster to support your analysis. Again, AnzoGraph is a massively scalable, in-memory, distributed RDF triple store that's extremely fast. We are the fastest graph database on the market today, both in query and load performance, with a ton of different analytics that are built in. And we'd love to hear from you to support the project that you're working on. So please contact us at info.anzograph@cambridgesemantics.com, and thank you for joining our video.